Analytical Chemistry 1, Lesson 31. Without a doubt, one of the most important roles that acids and bases can play in science is that of a buffer. A buffer solution is one that resists changes in the pH. It helps to stabilize the pH of a solution at a particular value. Biological systems generally occur in buffered solutions because the important chemical reactions that occur are pH dependent. For example, our blood is buffered to remain in the pH range between 7.32 and 7.42. If it were to drift outside the range, proteins would change their shape, which has been called denatured, and no longer perform their function. Ion channels that pump ions in and out of cells would also begin to fail. Untreated, this proves fatal. Someone who suffers with diabetes knows that an acidosis condition can arise, that the blood pH drops below the accepted range. Prompt treatment is necessary if they are to recover. Watch what happens to a solution's pH as we add an acid. First of all, what happens when we add a concentrated strong acid to a container of pure water? Take a 1 millimolar solution of HCl and add it dropwise to 1 liter of water. We have prepared the water so it has no atmospheric contamination and its starting pH equals 6.998. Recall that water's equilibrium constant at 25 Celsius is 1.007 times 10 to the minus 14. Using this precise value, the pH of pure water is just slightly below 7. The water does not have any additives that would affect its viscosity and surface tension, so 20 drops constitutes a milliliter, so that one drop is about 1/20th of a milliliter, or about 0.05 milliliters. Start adding one drop of this 1 millimolar strong acid to the water, and we'll swirl it around to be sure it's spread evenly throughout the beaker. Monitor the pH. Recall how back in lesson 24 we solved the equilibrium for strong acid and came up with a quadratic equation solution without approximations, except for ignoring activity as usual. Here are those results. The first drop decreases the pH down to 6.891, a pH of almost 0.2, a drop of almost 0.2 pH units. Recall our blood needs to be buffered to stay within the plus or minus 0.05 pH range. The second drop brings the pH down further to 6.790. Each subsequent drop makes the solution a little more acidic. We can continue, and we expect that each drop will lower the pH a little further. Note that this graph, as presented, only accounts for the addition of 1.5 milliliters to this 1 liter container. This curve is how it will appear as we continue out to 30 drops, which is 1.5 milliliters. If we were to continue until we added an entire liter, it would be like diluting the original acid by half, and the pH would be 3.301. A very small amount of added acid significantly changes the pH of water. If, as suggested above, we need to control the pH to ensure that our chemical reactions were occurring correctly, as is the case for all of our physiological processes, for example, then pure water would not be very useful. What if we already had a weak acid present in the solution? Let's imagine a 1 millimolar acetic acid solution instead of pure water. Let's again add 1 millimolar HCl dropwise and see what happens to the pH. The behavior of the pH when added to the pure water is shown again in the faded purple line. This time the pH begins at a much more acidic point because of the acetic acid. The pH is 3.907. We again add one drop, but this time the pH does not change, at least as measured by our pH meter that has 3 significant decimal places. We add another, and another, and we finally observe a pH drop of 0.001 units. After 6 drops, the pH has only dropped 1/1000th of a pH unit. When the same 6 drops were added to pure water, the pH dropped by more than a half a pH unit. The difference is a factor of 500. We carry on out to a total of 1.5 milliliters of added acid, and the drop in pH is barely measurable. It is about 0.004 pH units. At the same point, the pure water pH has dropped about 1.2 pH units. The presence of 1 millimolar acetic acid buffers the solution against large changes in pH. Here's the addition of 500 milliliters of the acid. It is at this point that the two solutions finally start to show a similar behavior. But the important point is what happens with the addition of small amounts of acid. In pure water, that would lead to large changes in pH, while in the buffered solution, the pH changes would be negligible. This is very important in many reaction situations. Now you might wonder why it behaves this way. Look at the acid equilibrium expression. Let's rewrite it and solve for H+. The hydronium ion concentration in solution depends upon the ratio of the concentration of the buffering acid and that of its conjugate base. When the HCl is added to the solution, those added hydronium ions react in the first place with the conjugate base and produce additional acid. The added acid begins to participate in the acetic acid acetate acid-base reaction. It is just converting a bit of conjugate base into the conjugate acid. Before any acid is added, the ratio of acid to acetate is 7.057. Once we add 1.5 milliliters of the HCl, recall that would be 30 drops. The ratio has increased to only 7.096. A solution is buffered when there is a substantial amount of both the acid and its conjugate base. The addition of another acid then converts the conjugate base into the conjugate acid. The addition of the base converts the conjugate acid into the conjugate base. The ratio of the two components of the buffer's acid-base pair slowly changes and gives rise to a very small change in pH. The solution's pH is buffered. As long as the added acid or base is not so much as to mostly consume one or the other of the buffer components, then the buffering action can be maintained. But if too much additional acid or base is added, and too much is determined by how much of the buffer is present, then the buffering action is exhausted. The acetic acid acetate buffer we have looked at is good, but the value of pH it can buffer seems to be fixed by the behavior of acetic acid. It nicely buffered a solution at a pH of about 3.9, but what if we needed to buffer a solution at another pH? We see that a solution that is formally 1 millimolar in acetic acid will act as a buffer around pH 3.9. But if you do the calculation, you will find that a 100 micromolar solution, now that is 1/10 the strength of our 1 millimolar solution, it would act as a buffer around pH equals 4.47. And a further calculation for a 10 micromolar acetic acid solution would buffer around pH equals 5.15. So is that all we need to do? Just adjust the formal concentration of acetic acid? Remember that a solution's buffering ability depends upon there being a good supply of both the conjugate acid and the conjugate base. When you add some acid to water, the hydronium ion accumulates, the solution acidifies, and the pH drops. But when you pour that same acid into a solution that already has a comparatively large amount of a weak acid in its conjugate base, then when the hydronium ion enters the solution, it reacts with the conjugate base to produce the weak acid. The added H+ reacts rather than accumulates. There is some H+ that's present, but the amount is controlled by the chemistry of the weak acid-base pair, not by the added acid. In this way, the solution's pH is buffered.